Hello and welcome to Chapter 9. Today we're going to look at Section 1, which deals with chemical reactions. So to begin with, we first need to understand what a chemical reaction is. And this is the process in which atoms of one or more substances rearrange to form different substances. Okay, and if you recall, we talked about this a while ago and we called this a chemical change. So some of the things that tell us that a chemical reaction has occurred would mean this delta, that triangle there is called delta. Delta T means that there's a change in temp. Sometimes you'll see that you get something that almost looks like a spark, and you'll get either heat off it, like maybe you feel a beaker warming up, or you'll get like that spark or flash of light. That's an indication of a chemical reaction. You can get changes in color. Sometimes things will change or have an odor to it. You can see like gas bubbles forming, kind of like in a soda, like a can of pop or something. When you see those bubbles coming up, that's your carbon dioxide bubbles. And then sometimes we also get formations of solids. So just to kind of give you a visual, right here in this upper right corner, we have this, we had two solutions that were mixed together and it created a solid. So that's an indicator of a chemical change. Something like rust shows us that we've had a chemical change occur. Here we have heat and light is given off, and the same thing with a matchstick. Okay, the matchstick is also changing color. You can see that it's turning from kind of like this light tan color or wood color over into the black, which also is an indicator of a chemical change. So when we're talking about chemistry, okay, scientists will typically use equations to show a chemical reaction. And again, we've talked about this in the past, but remember we have our products and our reactants, and a reactant is our starting substances. So those are the two things that are going to be mixed or put under pressure or heat added to them, or maybe they just sit there and they're going to decay, but essentially it's what your starting substances are. Then as the chemical change takes place, we end up with new products or new substances that are formed as a result of that chemical reaction. So when we look at our chemical equations, we typically use an arrow instead of an equal sign, and the arrow is going to show the direction of the reaction. So we can read the equation essentially as that arrow means reacts to produce or yields. So down here in this equation, I would say R1 plus R2 yields P1 plus P2, or reactant 1 plus reactant 2 reacts to produce product 1 and product 2. A lot of times in chemical reactions, you're also going to see symbols, okay, such as S, L, G, and AQ. Okay, these typically show us the physical states. Okay, so if I see that I have like an S and an L that are mixed together, I can see that that would be a solid and a liquid that were being mixed, and maybe they produce a gas. Okay, or maybe we get something in the aqueous form. Remember, aqueous essentially means that it's been dissolved in water. So that's what the AQ stands for. Now the physical states are actually very important because sometimes it will tell us what we're going to get, or it will give us clues about how our reaction is going to occur. Now when representing chemical equations, we have a couple different formats that we can use. Okay, the first one would be something like what you see here called a word equation. It says aluminum in the solid state plus bromine in the liquid state gives us aluminum bromide in the solid state. Now this equation is nice because it tells us what we have, it tells us the physical states of what we have that's going to react together and what it produces. However, it lacks the important information. It doesn't tell us how much or any of the ratio information, and it doesn't tell me if mass has been conserved or not. So although the word equation is nice, it lacks important information that I actually need in order to make this reaction happen. So let's look at a different format. We also have what we call skeleton equations. And a skeleton equation kind of looks similar to the word equation, except we're using our symbols. So we have aluminum in the solid state. Now Br2, remember bromine is a diatomic molecule, that's why we have that 2 there. So I have Br2 in the liquid phase yields aluminum bromide. Now this one tells me I have 1 aluminum and 3 bromines, which is nice, and it tells me that's in the solid state, but it still doesn't tell me how many aluminums or how many bromines I need and how many aluminum bromides it's going to produce. So the skeleton equation still lacks important information, and I can see that mass is not conserved. So what I mean by that is, remember, mass is neither created nor destroyed. It is conserved, but when I look at the skeleton equation here, I can see that I have 1 aluminum and 2 bromines, but over on this side, I have 1 aluminum and 3 bromines. So because I have 3 bromines over here, that tells me that this side is probably going to be heavier than my reactant side. So mass is not conserved, and we know that that has to be conserved. So this is going to take us to the third and final form of equation, and that's called a chemical equation. So in a chemical equation, this is an equation that will show the number of atoms of each reactant and each product on both sides of the arrows. Okay, so essentially this is kind of the key component that's been missing. This is where it's going to show us how mass is conserved. So a chemical equation is a statement that's used in chemical formulas to show identities and the relative amounts of substances involved in a chemical reaction. So when you look at this here, I can see that I have 2 aluminums. So if I list out my aluminums on this side, and I'm just going to draw a line right underneath the arrow. So aluminum equals 2. Bromine, I have 2 bromines down here, but I'm going to multiply that because I have 3 of those diatomic molecules, which means that I have 6 bromine. And then over here on the other side, or on my product side, I have a 2 in the front. So it's kind of like math, where really that 2 is being distributed onto everything. So I have 2 aluminums, and my bromines, although I have 3 down here, I'm multiplying that by 2, so I really have 6 bromines overall. So you can see now that mass has been conserved because I have 2 aluminums and 6 bromines. This is how I know that I have a true chemical equation. Now, in order to balance equations, you must have the correct coefficient in the skeleton equation. The coefficients have to be whole numbers, and the coefficients are going to describe the lowest whole number ratio. Okay, so sometimes when you balance equations, and I do this myself, sometimes you just kind of get on a roll, and when you stop and you look back and you notice that everything can be divided by 2, then you need to go and take a 2 out of everything. It has to be the lowest whole number ratio. We do have a few steps when balancing equations. Okay, the first step is going to be to write the skeleton equation. Okay, so that would be with your, with your element symbols. And the one thing that I cannot stress enough is please remember those 7 diatomic molecules, because if you do not include the diatomic molecules, it's going to make your balancing very, very difficult. Okay, then we're going to want to count the number of atoms in the reactants and count the number of atoms in the products. Okay, and I did that on that last slide when I like to draw a line straight below the arrow, and then I like to do that on either side so I can see how many that I have. Then what we're going to do is we're going to start changing the coefficients to make the number of atoms equal. Make sure that we have the lowest coefficient in the lowest ratio. And then we'll, of course, are going to just double check our work and make sure that everything works out. So let's go ahead and look at a few examples. So for example 1, it says write a chemical equation for the reaction between hydrogen and chlorine that produces hydrogen chloride. So in this example, it does remind you that hydrogen is a diatomic molecule and chlorine is also a diatomic molecule. So I have H2 plus Cl2 yields HCl. So this is step 1. Step 2, if you go back to that last slide, says to list out the number of atoms in both the reactant and the product side. So again, I like to just draw a line straight down, and I'm going to list my hydrogen and my chlorine. Now, even if they don't appear in the same order on the product side, I like to have hydrogens across from hydrogens, chlorines across from chlorines, and so on. So what I do now is on the reactant side, I see here that I have 2 hydrogens and 2 chlorines. So I'm going to go ahead and write a 2 here and a 2 here. And on the product side, we have 1 hydrogen and 1 chlorine. And I know that because neither one of those have a subscript. So what I'm going to do now is I'm going to come up here, and if I write a 2 in the front of the HCl on the product side, what that does is that's going to change my number of hydrogens to 2 and my number of chlorines to 2. So now, because my hydrogens both have 2 and my chlorines both have 2, that tells me that I'm balanced, and I can see that I have 2 chlorines here, 2 hydrogens here, 2 chlorines here, and then I end up with 2 compounds or 2 molecules of HCl. And for our last equation, it says write the balanced chemical equation for the reaction in which aqueous sodium hydroxide, so aqueous sodium hydroxide is NaOH, and I would put the states, and aqueous calcium bromide, so CaBr2, and this again is aqueous, and it says reacts to produce a solid calcium hydroxide, so CaOH2, and again this is aqueous, and aqueous sodium bromide, so NaBr, and this is also aqueous. Okay, so this is my skeleton equation. Now, you are going to have to remember your rules from chapter 7 and 8 on naming ionic and covalent and acids so that we can write these correctly. So now what I'm going to do is I see that I have 1 sodium over here. So that's 1. And when I come over to this, my product side, I also have 1. I would say a majority of the time, if you have a polyatomic ion, that polyatomic ion is going to stay together. So in this case, we're going to try it. So for hydroxide, I have 1 hydroxide. And over on this side, I can see that we have 2 hydroxides. On the reactant side, I have 1 calcium. And on the product side, I have 1 calcium. Then on the reactant side, we have 2 bromines, and on the product side, we have 1 bromine. So for me, I kind of like to start where my issues are. I have 1 sodium on either side. I see on my product side, I have 2 hydroxide, so that means I'm going to have to come over here and at least put a 2 in the front of NaOH. Now when I do that, I end up with 2 NAs, and so 2 sodiums and 2 hydroxides. So now I'm no longer balanced on my product side because I have 1 sodium, and so if I come over here and I put a 2 in front of the sodium, now I have 2 sodiums, and that also affects my bromine, which means I have 2 bromines now. And so now if I look, I have 2 sodiums, 2 hydroxides, I have 1 calcium on either side, and I have 2 bromines. So that tells me that everything is balanced, and my correct balanced equation can be seen right here. Please let me know if you have any questions. Otherwise, I hope you guys have a great day, and I'll talk to you in class.